to have today Tom Mountford from EPFL, École Polytechnique Fédérale de Lausanne. And so he will speak about invariance principles for Markov cookie random walks. So yes. Thank you, Tom, for accepting.
It's my pleasure. Okay, so I now pass to my slides straight away. So. Okay, so first I would like to thank Claudio for inviting me to renew my acquaintanceship with Brazil. So this, as we say, is joint work with Elena Kosygina and John Peterson, and it's recently been published in PTRF. It's quite a long paper, but the idea is pretty straightforward. Okay, so the talk is just in 3 parts. First, I'd like to talk about cookie walks, what a cookie walk is, a little bit of history, but I mean, Markov cookie walks in particular, they're not a regular part of, not mainline probability, so it bears going over what I'll be talking about. Then after that, we go to the second part, which is just a discussion of the Ray-Knight approach. The important papers for me are the papers by Todt and Badevin and Singh, which use the Ray-Knight approach. And then finally, the last part will be just me talking about the diffusion approximation and what we do, what's new for us. Okay. So, to recall, for a cookie, I'm going to be talking about cookie random walks on Z, even though the first papers were about processes on Z walks, random walks, on cookie random walks on ZD. I'm going to talk about cookie random walks on Z because this Z is a tree, and this enables the Ray-Knight approach, which is not available in higher dimensions. Okay, so we have at every site Z, little z, we have omega Z, which is just going to be a sequence of values, first as a sequence of positive probabilities, which give the probability of jumping to the right on the ith visit. So that's in this sense here. So we will assume that the omegas considered as a random vector are IID. This is not necessary, but it's certainly a very convenient assumption. And we'll have again, often we don't need this, but we have this uniform ellipticity assumption. As we will see, this is a bit irrelevant in what we do, but I'm talking about a little bit of prehistory. Okay, so we start off our cookie random walk at 0 at time 0, and then, as we've said, the cookie random walk evolves. It's a nearest neighbor walk. You go from, if you're at xn, you go to xn plus 1 or xn minus 1 at time n plus 1. And the probability of moving to the right is just given by the cookie, given everything that's gone before it, is just the nth cookie at the current position xn. So for z equals xn, you look at the cookie, the lnxnth cookie, which is just the number of visits you've made, the X process has made to the current site xn up to the current time, including 0. Okay, so this process, you can see, is not going to be a Markov process unless you have some very strange assumptions on the cookie pile or trivial assumptions. It's not going to be a Markov process, but it will have lots of good Markov properties, as we will see. Okay, so this was introduced by Benjamini and Wilson in 2003, and here you just had one cookie which had a certain value, strictly greater than a half, one cookie at every single site, and the question was, particularly in 2 dimensions, is the process going to move if the cookie makes you bias towards the right, will your process be transient? And they proved that it was. And then Martin Zerner in 2005 broadened the idea to have just cookie stacks, and you had he made a lot of use of translation invariant systems and the ergodic theorem here. Okay, so for us, well, typically at this point, people were talking about cookies which were always biased due to the right, if you're looking at Z, and often we assumed that there were just a finite number of cookies, which is another way of saying that for every Z, WZI was equal to a half if I is bigger than M or great. Okay, and so in either case, if you have this quantity would be well defined, delta, and the really key idea, and it goes back a long way, but this is something we use a lot. The key approach was from Badavin and Singh, who were able to show, using an approach that I'm going to detail, that you would move to the right if and only if delta, this number here, was greater than 1, and you would escape ballistically. It's to say, xm would be of order n if delta was greater than 2, strictly greater than 2. Okay, so our model, the model we will be thinking about, is not a finite range cookie, typically. What we have is, well, I say irreducible, that's just for simplicity. What we want is that omega z is a realization of a Markov chain on a finite state space, you have this Markov chain on this finite state space, and I say irreducible, but really what we need is that there's one and only one stationary distribution, and the omegas now don't really, you can think of them as probabilities, but they're not really. What we have actually is a function p from the states in the Markov chain to 0, 1, not including 0 and 1, and they are and they give the probability. So if we go back here, instead of it being the probability of xn being xn plus 1 given all of these guys, this would be p of omega xn. Okay, so we have these. We have the probabilities work like this. It's similar to the previous case, but we have a function p of where you are in the Markov chain. Okay, and we're going to suppose in this talk that the unique invariant distribution for this Markov for the Markov chains pi satisfies the integral of p with respect to the measure pi is just a half, because if you don't have that, then it's pretty easy to see that your cookie random walk, if the integral of p is greater than a half, you're going to move off to the right with probability 1. If the integral is less than a half, you'll move to the left. So in a very real way, this is the only interesting case where the mean with respect to the equilibrium of the cookies is a half, is fair. Okay, and we suppose that initially the first cookie, these are going to be IID according to some probability measure eta. Eta could be pi, doesn't have to be. Typically, it's not. It's just a probability measure on the state space. So basically, what we have are the cookies evolve according to a nice Markov chain, and they start off with initial value eta. Okay. So this was addressed and studied by Kosygina and Peterson within 2 papers. Okay, the next bit of background material, which not everybody knows, is BMPE, Brownian motion, perturbed at extrema.
There is a question by Milton.
Okay.
He asks, just to have an example in mind, is this like the rotor-rooter model, but with
right? This is it. That's exactly a good thing. It's very like that. The rotor-rooter is it's sort of deterministic in its evolution, but yes, this is that's a good example. I mean, the rotor-rooter would not be quite having this, but it's very it definitely rotor-rooter could be taken to be an example of this. In fact, I think Kosygina and Peterson were inspired by the rotor-rooter to generalize it. Milton, is that satisfactory?
Yeah, sure.
Yes. Thank you.
Okay. Sorry. So we have this. Just to give a very brief overview of a Brownian motion perturbed at extrema. It's just a solution of this equation, typically starting at 0, where B is a Brownian motion, a standard Brownian motion. Okay. We'll be interested in solutions of this where B is which are multiples of this, multiples of such a process, which essentially are the same process. So here, the parameters alpha and beta have to be strictly less than 1, or the process isn't defined. And that's just because if you suppose alpha is positive, your process, your W process moves around, it moves like Brownian motion until it gets to either a maximum or a minimum value. Then if alpha and beta, let's just take alpha. If alpha is greater than 0, it gets a kick. It gets a kick to the right. And actually you can see that if it's not so difficult to see that if you're getting a kick by more than 1 unit per time you get there, then you essentially keep going to the right. You just take off. Okay. If alpha is, let's say, if alpha is 1.001, then there's no process. Or if alpha is 1, there's no process. But if alpha is minus 1,000,000, we're quite happy with that. We're quite happy that you're pushed away from the maximum towards the center. That's fine. But to be pushed away, too much away from the center, the process won't be defined. Okay, I'm not really going to get too much into the technicalities, but here are some references. Okay, but why this is relevant, we're going to see is, well, first of all, we need this terminology and these models to talk about our process, our model. So if I give you this Markov chain and this function P, then from this, we can compute 2 processes, delta, delta tilde, and the process is going to be recurrent if both delta and delta tilde are less than or equal to 1. Okay. Now, actually, if delta is equal to 1, it's a bit interesting because if delta is equal to 1, this is a boundary case, and the process is recurrent, but it rescales to a process naturally to a process that is transient. But we're not interested in this critical case. We're just going to look at the case where both these parameters, delta and delta dash, are between -infinity and 1, which is what we assume of our alpha and beta. And in this case, our process is going to be xn, if we our random walk, our cookie random walk, if we normalize it diffusively, it converges weakly to this multiple in sigma squared. I haven't said what it is, but that again is derived from the Markov chain. So it's just this multiple of this Brownian motion perturbed at extrema. Okay. Now, I'd first like to just say, you know, ours is not the first result of this kind, but the first result of this kind was with Dolgepiat and Kosygina, and they considered, well, they considered a more general class, but they considered, let's just take it to be a finite number of cookies. And they said their delta is the delta originally defined, the sum of the total biases. And they said if delta is between -1 and 1, then, well, we knew that the process was recurrent, but the process does converge to a Brownian motion perturbed at extrema. And this is a natural result. You can see this in the case where you have no finite number of cookies, because, you know, I'm not exactly proving this, but you can see that if you're away from the maxima, typically you've visited your sites. The sites you visited have been visited quite a few times. And you can, if there are a few sites there where you haven't visited them all that much, that's not such a big deal. But typically, in the bulk, away from the maximum and the minimum, you are going to be moving essentially like a random walk. Okay, so, but when you get to find new territory, you get to a maximum, you explore new territory, you're eating cookies. The cookies may push you to the left or the right, but they are going to push you in more or less the same way, in a consistent way. And so the strategy here, which will not be available to us, was essentially, the strategy was to say, well, essentially you've got, if you look at it, you look at the conditional expectation, you could say you have a natural martingale, which is converging to Brownian motion. You have a consistent push. You can have a law of large numbers on the push, and you can then show tightness, and that's it. Okay, I mean, I'm being very quick. The proof wasn't that easy, but you know, but it went along those lines. A result of a similar character for our process was established by Kosygina and Peterson in a second paper, but their CLT, it relied on the cookie stacks being periodic, which meant, you know, by that I mean, you know, you go deterministically from 1 to 2 to 3, from I to I+1 with probability 1. And this had the advantage that if you're looking at the amount of drift or the bias resulting from one site, that's always going to be bounded. So that enabled them to do a couple of things that weren't available to us. Okay, so that ends the first part, and now the second part would be talking about a review of Ray-Knight ideas. So, I mean, there are lots of Ray-Knight. Well, there's more than one Ray-Knight approach, but I'm going to be talking about. I'm going to be using mostly the Ray-Knight approach used by Badavan and Singh, which looked at a cookie random walk up until time tn, where you first hit n for the first time. Of course, your cookie random walk in generality, well, for them, they were considering positive cookies, so you would hit n. If your cookies could be negative, meaning push you to the left, cookie values less than a half are allowed, as well as cookie values greater than a half, then this needn't happen. But nonetheless, you could say, let's suppose it did happen, if it did happen. So that's a sort of little qualification in this. But then you could say to yourself, well, and here, let me just do a little bit of sketching. If you get to n at this time, and now you look at the number of moves from n minus k to n minus k plus 1, I think it was, yes. You look at this number of moves. So obviously, if k is 1, the number of moves is 1, because you hit this for the first time. But if you look at this number of moves, you can sort of say, the argument, the basic Ray-Knight argument, was to say, what's been happening at this at this level? You move away, you come back, you move maybe to the left, you come back, and so forth. Well, now here, we could say, well, let's have a look at this guy. Suppose you made L moves from n minus k to n minus k plus 1. Okay, then actually what you're doing is you can think of the cookie as being your motion is dependent on randomness, which is located or peculiar to the site n minus k. You can say we are looking at this site here. We're looking at this site here, and we're looking at the number of. We can ask ourselves, how many moves did we make to the left before we made L moves to the right? Okay, and that is going to be, well, if there were no cookies, that would be the expected value would be around L, would be L, actually would be exactly L. Okay, but we have this bias, we have the cookie bias. So if you're biased to the right, the number of moves you make is going to be actually L minus the number of cookies, if L is large. Okay, the number of cookies at this site, n minus k. Okay. Okay, assuming L is large compared to n, it's going to be like this. And so you say, so we will have made about this number of moves from n minus k to n minus k minus 1, not plus 1. Okay? But now you say, well, if you made L minus this number of moves to the left, you must have made this number of moves from n minus k minus 1 to n minus k plus 1. And it's plus 1 because, of course, you've started off at 0. You're running it until you've gone to n. So the number of moves you make from going from here to here is equal to the number of moves you make going from here to here plus 1. So that's where this very important equation occurs. And from this, you can sort of say, well, you're looking at the variance, and we have this variance, and you can get very good information. Now, the point is, what we have here is that our L, as we work backwards, we're looking at the first time we went to n, we're looking at L, which is in reverse time, L1, L2. This is a Markov chain. This is going to be a Markov chain on n, the value n. Okay. And the point is the following. You can ask yourself, well, is this Markov chain recurrent or transient? If it's transient, then by the time you get back to 0 after n goes, your value should be very, very large. And that's telling you the chain isn't transient. As n goes to infinity, the number of visits to things that are happening at 0 is getting larger and larger. That's transient. Okay. On the other hand, if it's positive recurrent, then the number of moves you make here, so it keeps a reasonable value. The number of moves you make around here is going to be of order 1. It's going to be bounded. And that means your process has to be transient. Okay? And if the invariant measure is nice and integrable, then the number of moves you've made, maybe I'm counting just the moves in the right direction, but that's essentially going to be the number of moves in total divided by a half. That's going to be that's going to be of order n, and so you're going to be moving ballistically. Okay, so this was a very good, nice, beautiful resolution of this problem by Badevin and Singh, and this is going to be key to us. Okay, and here again, the work of Balint Tot is very, very important. So for us, and this goes back to Tot, we are going to actually try and do the same thing, shall we say? Let's try and do the same thing. So we look at the first time we get to n, but now if we're looking at the number of moves we made from n minus k to n minus k plus 1 here, well, now we're going to use we have to introduce a Markov chain, just like Top did, which is we're going to say, let's consider, instead of our Markov chain, which evolves at site n minus k, let's look at the Markov chain where we just look at the state of the Markov chain at time after the Markov chain has moved, let's say, to the right for the kth time. But actually we look at the Markov chain at value sigma k, the kth move to the right, plus 1. Okay, this is a different Markov chain on these integers. Okay, and this will have an equilibrium, which won't be the same as pi, typically, pi plus. And we can do the same if we start looking at the Markov chain one move after it's moved to the left for the kth time. We have two distinct Markov chains here, which obviously are related to the original Markov chain, but they're different. But they're different. Now, what I want to do is I want to use this to talk about the functions r plus and r minus, which are going to be very important for this talk. Actually, what I'm going to say is, let's just look at the chain, and I'm not going to think about Ada just yet. I'm just going to think of the Markov chain starting off with value I, and I'm going to look at when you make look at the number of moves to the left that the Markov chain has made. The Markov chain minus by after n moves to the right minus n. This n is the same here. This n is this n. Okay. Now this is going to converge. You can see it's going to converge. Actually, that's not too difficult. The expectation of this is going to converge to a number I'm going to call Ri plus. Okay. And just as before, if we're working our way backwards, we can see then if Lk is large, the expected value of Lk plus 1 Lk is going to be like this. Okay. The variance is going to be some number, sigma squared, Lk, approximately, to first order. Sorry, just to repeat, the NKs are, the LKs are again, the number of moves you make from n minus k to n minus k plus 1. Okay, and now, if I'm looking at, oops, excuse me, what have I done? Okay, sorry. If I'm looking at the Markov chain when it moves to the right, and I look, when it moves to the right, if it starts off in pi plus equilibrium, when it moves to the right for the first time, and then when it comes back at this point, it's still going to be in pi k equilibrium. Okay, this is just the usual transformation. You look at it until you make a move to the right, then you come back, you're in equilibrium. So from this we see, well, because pi p is a half, you're going to make as many moves to the right as to the left in the long run, at least in expectation terms. That tells you that pi plus, the integral r plus, has to be 0. Okay, the overall bias has to answer out. You can't have a bias because otherwise you have an equilibrium. You apply the ergodic theorem to your Markov chain, and you're going to have a bias towards moves one way or other, to moves to the right or moves to the left. And this statement here says you don't have a bias. So we have this is 0. And in exactly the same way, if you look at the Markov chain when you move to the left, you have r minus, this is 0 for the same reason. But it's very important to realize pi plus of r minus, pi minus of r plus, they don't have to be 0. There are restrictions on them, which may be a bit mysterious. And in fact, we have the integral of r minus with respect to pi plus is the integral of r plus with respect to r pi minus, and sigma squared is given by this, which was nice, but it turns out actually to be very, very important, property D. But for me, it was just a curiosity. And the functions delta, which define our Brownian motion perturbed at extrema, are given by these results here. Okay. So that. And now, well, sorry, I should say, if we're looking now at LK here, how LK evolves, there's two things. You have this and you have this. So essentially, when you make LK large and you renormalize LK, as we say, LK plus 1 is going to be equal to LK as you work your way backwards, plus some centered something of order, a centered random variable of order square root of LK times square root of LK. This would have variance 1, or sigma, sigma. And you're going to have plus this number here, which I'm going to think of as 1 plus an R value, RKI. Think of it as dt. Okay. The reason I write it this way is because this is then, we could expect that if we look at LNT and we divide it by n here, we should expect this to behave like something like a process x of t, where dx of t is going to be square root sigma square root x of t db t plus some constant d, bad notation, but there it is, sorry, d for dimension dt. Okay, and that is to say, this is going to be, we would expect this to be like a Bessel squared process. Okay, and we'll see, yes, this is indeed the case. So this is the equation for a Bessel squared process. This is the formal equation where sigma, your sigma is 2. And you have this Bessel square. This is the equation for a squared Bessel process of, well, d is, it doesn't have to be integer for this to be a well-defined process. Okay, and now I'd like to talk about just the Rey-Knight theorems for Brownian motion. So if you look at the local time at a position A, I'll take it to be positive just for definiteness, it could be anywhere, and you look at when the local time at A is greater than B, this is a stopping time for Brownian motion. And this is the Rey-Knight theorem. So the Rey-Knight theorem says, if you look at the local times, I start off by Brownian motion at 0. I'm going to run it until the local time at A is B. The local time here is B. Then you can ask yourself, what are the values, or how do the local times elsewhere behave? Well, if you look at the local time at this point, this random time here at tau AB, you look at these local times here. As you move in this direction, it's going to be a Bessel squared with dimension 0. Starting off at B, starting off at value B. If you move in this direction, you're going to actually see, you're going to get, as you move in this direction, it's going to be, but you're moving time in this direction, so it's going to be, you're reversing time on 0A, it's going to be a Bessel squared with dimension 2 until you get to the origin, okay? After you get to the origin, it's going to behave, as you move in this direction, as a Bessel squared 0, which starts, it's continuous, so it's a concatenation of these continuous processes, but this is going to die out because, of course, it's going to hit 0, of course, because, and this will hit 0, of course, because at a finite time, the range of a Brownian motion is finite. Okay? And again, you might ask yourself, why do we have this Bessel squared 2 and we have Bessel squared 0 here? And that comes from the fact that if you're looking at I'm just going to look at it in terms of cookie random walk approach, but if you're going beyond here, at this time, we have the number of moves to the left from, call it A plus K to A plus K plus 1, have to be the number of moves from here back again, okay? Likewise, if you start off at 0, the number of moves from here to here have to be the same as the number of moves from here to here, because you're ending up to the right of the origin, okay? You're ending up at A, because you're looking at it at time tau AB. But in here, the number of moves that you make as you go from here to here is going to be the number of moves the number of moves you make from here to here is going to be the number of moves from here to here plus 1. So that's giving a little bit of a kick here, which is why this is a Bessel squared 2 process here, okay? And of course, this is crucial to our project, but we have these analogous Rey-Knight theorems for Brownian motions perturbed at extrema. It's not particularly important. Well, I mean, it is important to our project, but we get these results. But the basic idea is that you start off at 0. You look at, let's say, I mean, A could be negative, of course, but you look at the first time. Your local time gets to be B here. Then beyond it, you have a certain Bessel squared process. Afterwards, you have a different Bessel squared process, which depends on the alpha here, on the beta. And here, in between, you have another Bessel squared process given by this. Okay? But it's not going to play a crucial role in these, in what I'm going to talk about. So now I'd like to see how this transforms for our local times. When we're looking at the Markov chain random walk, we get an analogous situation. We look at the Markov chain random walk. When you move, which is like local time, you move from x square root of n to x square root of n plus 1 for the y square root of nth time. Okay, and we're going to look, well, I'm changing the notation because before we were moving backwards, now I'm moving at LK, I'm moving LK forward. But here, we just can argue that we have the LK plus 1 given LK, it's going to evolve in this way. And you're going to have the variance is always going to be sigma squared LK. Here, if you're looking at K beyond it, it's going, if you're looking, this is at K less than minus X square root of N. So here's 0. Let's suppose this is X square root of N. We've looked at what happens. You look at when this is Y square root of N. You look at what happens as you move to the right. As you move, then you move along here, you're going to get this sort of behavior with a 1 here. And again, always the variance is sigma squared. So what's going to happen is actually, when you look at this for the first, you look at this and you do this, the natural renormalization by square root of n, but it's square root of n by time as well. So it's not diffusive because we're looking at squared Bessel processes. But what we have is we are going to get in the limit exactly this kind of behavior, the kind of behavior exhibited here. We're going to get that kind of behavior for our processes. For the what I call them local times, they're really half local times because I'm just considering the moves you make to the right. Okay. So now, the next important ingredient is that for our walk, what we're going to see, what we can prove, it's not actually that difficult to prove, but the walk is complicated. We're moving around, okay? But if we're at a position here, if you look at the Markov chain to the right of where you are, this Markov chain has moved this way and that. But then, because we're currently at this time n here, the last move the Markov chain made, was a move to the left. So actually, the distribution to the right should be pi minus, because you've just made a move to the left. The distribution of the next cookie, the available cookie should be pi minus. Likewise, if you're to the left of it, your last move necessarily was to the left. So you should be pi plus. So actually, here we have, well, a typical site morally to the left is in pi plus, to the right is pi minus, as long as you've made a good number of moves. And actually what we have, we need something much weaker than this. What we have, well, what we need is just that we can say, if you look at a scale smaller than square root of n, let's say n to the quarter, there's nothing special or subtle about this choice, it's just a number less than a half. The averages of the R processors, we can prove everywhere, should be very close to the average for pi plus, for both functions. And to the right, this is my mistake. This is, I made a mistake, this should be a minus here. To the right, if I is an interval within here, and I is of length n to the quarter, you should have this. You should be very close to R plus. Now here you might think, well, if you're really, really close to the maximum, surely this approximation is going to break down. And that's true. This approximation will break down close to the maximum, but we're talking about something very close to the maximum. So n to the quarter, if this is the maximum and you have an interval which is the maximum and then the maximum minus n to the quarter, basically the effect of the maximum is going to be very, very small, much smaller than n to the quarter. So most of the sites will be in this pi plus regime, pi minus regime, and you will still have this result. So in fact, you have this at any time outside, unless something has really badly gone wrong, you will have this averaging property. So actually, what that means is when we look at these LKs like this, we can actually get a diffusion approximation, not just for these special times when you've made a certain number of moves at a particular site to the right for the first time. Okay, so what we can say is, and I'm just going to look at the situation. I'm going to look at the situation of our walk, and I'm going to look at these times. This is a coarse graining approach we employed. So I start off at the origin, and I look at when you get to epsilon square root of n minus, you move by epsilon square root of n. And then from here, I look at the next time you move, and so on and so on. So this is a coarse graining, and suppose I'm at time x tnk, t epsilon nk here, okay? And I suppose I'm in the bulk. Suppose I'm in the bulk. By that, I mean I'm far away from the maximum value, and the minimum value, okay? So in that case, we would want to show.
We can't see anymore your screen.
Sorry?
We can't see anymore your screen.
Oh, okay, hold on just a moment. You can't see the screen anymore? Okay, let me just, can you see it now?
No.
Oh, gosh. Okay, hold on. I'm going to stop the screen and then restart it. I'll try that. Share screen, okay.
Yeah, now it's fine.
Okay.
Yeah,
It's good.
good.
Okay, thank you. Okay. So the point is, if we're far away, when I get to xtnk plus 1, xtn, I'm dropping the epsilon, we would expect, with probability more or less a half, this should be this plus square root of n, with probability approximately a half. Yes? If this is going to be a Brownian motion perturbed at extrema, if our result is true. Well, at this point, our argument is kind of this, maybe the stupidest way to say this probability is about a half, but what we do is we look at Tn, let's just say Tn plus 1, Tn minus k plus 1, which is the first time after Tnk that x m is equal to x Tnk minus epsilon square root of n. So we're going to look at the process. We're going to look at the process starting here, and we're going to look at it when we first get to here. Okay, maybe we've got to here first, maybe not. Okay, but the point is, from this, we can say to ourselves, well, if we look at the number of passes we've made from here to here, as we move along, this is going to be acting as, I'm going to look at the LK, where K is greater than or equal to 0, starting off here. As we move it, we expect LK, the expected value of LK plus 1, as we move between 0 and epsilon square root of n. LK plus 1 given L of K, this is going to be, well, it's going to be 1 plus R plus R plus I plus LK, and the variance, you can say, is going to be sigma squared LK. But this I's, we know, because we have this property here, everywhere you have this averaging property, that's going to say that as you move from here to here, L n t divide the square root of n, square root of n. This is going to be like a Bessel squared with, it won't really depend too much on, sorry, it's going to be like a Bessel squared as you move here, L t square root of n divided by square root of n. As you move between for t less than epsilon, this is going to be like a process which is dx dt is going to be sigma dx plus 1 plus the mean pi minus pi plus, sorry, r minus. So this should be r minus, my mistake, r minus here, r minus. Okay, this should be an r minus here. Okay, and the point is, this 1 plus pi plus r minus is actually, if you look all the way back, it's this. So this is going to be, there's a 2 here, but it's sigma squared. So actually, if you do the calculations, I'm moving a bit fast, but actually, what you have is on this region, this is going to be like sigma squared times a Bessel squared 2 process. Now, as you move along this way, now we're in pi, the original process is in pi plus territory. As you move along, you're looking at the you're looking for the R plus guys here. That's going to be a mean. Sorry, this is going to be pi minus. Sorry, pi minus. The drift is going to be pi minus operating on R minus, which is going to be 0. So on this region here, you're going to be like a sigma squared, Bessel squared, 0 process. Okay, which is what I'm writing here. So actually, this is what we get. We have factors 2. The factor 2 comes from the fact that actually we don't really have a local time. We have half a local time because I'm looking at moves in one direction. But what we have, therefore, is because of this diffusion approximation, we can argue, it's a very, maybe, a bit complicated argument, but we can argue that you have a chance because along here, the local time is like a Bessel squared 2, then it becomes a Bessel squared 0. Now, this process, if it dies out before epsilon, that means you hit minus epsilon square root of n before you hit epsilon square root of n. If it doesn't die out before that time, you hit epsilon square root of n before minus epsilon square root of n. And we know from the Raynight theorems with these processes for governing the local times, we know the probabilities are half. So this result tells us, this diffusion approximation tells us that in the bulk, we are going to move approximately to the left with probability half and to the right with probability half. Okay, that's fine. And now you ask yourself, what happens when you're not in the bulk, when you're not separated from the maximum and the minima? If you have this, you have a maximum here. Well, it's a bit more complicated, but the same basic argument works. We can go right back to the Raynight theorems for the Brownian motion perturbed at extrema. The diffusions work out correctly, and we can say not just that our process moves to plus down epsilon square root of n before moving up with epsilon square root of n with the right probabilities, but also the evolution of the maximum is going to be the same. It's going to be the right one. So we have this from this, we can coarse grain and get the convergence result we want. So effectively, that's all I have to say about our argument. I mean, it ran to about 60 pages, but the idea is very, very simple. Okay, so.
Well, thank you very much, Tom. So maybe I think we can unmute our microphones and thank Tom for this very nice talk.
Thank you.
And now we are open for questions. Other questions?
Well, one point I would make is just to clarify something is in this kind of motion, you think of pi. If you start off with product measure pi, the real equilibrium of the Markov chain, you might think that that's a Brownian motion because you would get a Brownian motion which isn't perturbed, but actually it will be perturbed. Well, it depends on the Markov chain, but typically that will be perturbed. The real equilibrium for your process is pi minus to the right, product measure pi minus to the right, product measure pi plus to the left, and the equilibrium measure, which is a half pi plus and a half pi minus for the cookie where you actually are.
Yeah, so I have two questions in this direction. So the first one is that, well, your method relies on the fact that you are nearest neighbor, but would you believe that you will find something different for non-nearest neighbor jumps?
Yeah, I would actually be very surprised if something different occurred. Yeah, because I mean, but yeah, you're right. I don't know how to deal with non-nearest neighbor because that's going to blow up the Raynight approach.
Yeah.
So, and I'm not aware of a nice, of a robust way of handling that.
And then if you take an asymmetric, would you expect to find also, if you sit at the walk, that your environment will reach equilibrium?
Yes, because you could, well, you will have, I mean, in Kosygina and Peterson, they tackled the fact that you will have these nice regeneration points. And when you move, let's say, to the right, you have nice regeneration points and things are nice around there. Yes. Yeah. I would also say, I mean, with this process, if we started off in what I call equilibrium, I think you can, we've talked to Kipnis-Varadhan experts, and they say, yeah, you would probably get Brownian motion. You could do it. We think we could do that. But for us, first of all, we have perturbations at extrema, so that wouldn't work per se. But secondly, we need something quite robust to deal with things that are close to equilibrium, but not quite. And Kipnis-Varadhan is not so easily, it's not so robust in that way. Yeah.
Well, thanks. Questions?
So I have a question.
Yeah.
So do you know if there is do you know if there is some sort of martingale characterization of these processes, and if you know if there is a characterization, why is it's not useful for this type of problems?
When I say a martingale characterization of the cookie random walk.
No, or the limiting process. I was thinking,
the Brownian motion.
The usual way.
The Brownian motion.
Yeah,
because extreme. Yeah. Well, we have. Yeah. We have this underlying Brownian motion. So if you take, yes, you've got your process minus the alpha and the beta. That's a martingale. But for us, what made this difficult was the interaction. The fact that the fluctuations on the as you go from one Markov chain to another are not independent. Things are so you're going to have these, which is why your sigma squared is not typically going to be the one. So the randomness is a bit complicated. You can, I mean, from what I understand of your question, Milton, it's you can absolutely move this way if you have the. I mean, to me, this is similar to what Dolphy-Gyat and Kosygina did when you run out of cookies. That there they could just simply say your motion is a martingale, which we can see when you renormalize it is essentially a Brownian motion, because essentially you could prove that most of the sites you visited, you will have visited a large amount of time, and that the sites you visited just a little bit before moving to the left and the right don't really count. So you could actually push this through. That's what they did. But we really couldn't see how to make this work in our case. I mean, this is why in the other result I mentioned by Kosygina and Peterson, they could deal with, they had to do a fair amount of manipulation, but it was something along these lines in the periodic case, because in the periodic case, you could control the variation as you moved from one cookie to another, with doing your as your particle moved, as your random walk moved. So you were able to actually use the fact that there is this martingale, this Brownian motion, to get somewhere. It wasn't quite so straightforward. I didn't think, but it was along those lines. I mean, their argument when they'd assembled all the details and the technical results needed really was about 3 pages. So that was simple, but we really couldn't see how to do that in our more general case.
Okay, thank you, Thomas.
Any other question? Well, if there are no more questions, I think we should unmute again. And thanks, Tom, again for this nice talk. Thank you, Tom.
Thank you. And could I just say, I hope to see you all soon. Really soon. Really see you.
Yeah, let's hope to.
Okay.
Okay. Many thanks. Bye-bye.
Thank you. Bye-bye.